All right, hi everyone. Welcome to this week Autonomy Talks. Thank you. Thank to the today's speakers for the nice tune. So today is a great pleasure to have actually two speakers. So we are we have a new kind of talk. We have Dr. Quentin Boehler and Simone Gervasoni. So something about them. Quentin Boehler is a senior scientist at the Multi-Scale Robotics Lab. And prior to joining the Multi-Scale Robotics Lab, he actually got a Master of Science in Mechatronics from the INSA Strasbourg, a PhD in Robotics from the iCube Lab at the University of Strasbourg. His research focuses on magnetic actuation for medical robotics, and he is the robotics expert of the group, as Simone was saying. Simone, instead, is a PhD student at the Multi-Scale Robotics Lab. He actually comes from Ticino, so he's a fellow Ticino guy. He did his bachelor's and master's both at ETH in mechanical engineering, and he worked focusing on polymer composites printing and also on aerospace systems. He is now the lead designer for the electromagnetic navigation system you will see today. And he's also interested in general in additive manufacturing and rocketry. Today they are gonna show us some of these magnetic actuation and navigation work, and we are really happy to hear what they're gonna talk about. So the stage is yours. Go ahead.
Thank you. So thank you all to be here today. So as it was said today, we're gonna be two-person presenting. I'm gonna introduce a bit the subject and guide you through some, I would say, simulation and theoretical background on magnetic actuation, and Simone is gonna present more practical results on the design and evaluation of the systems we're interested in today. So my name is Quentin, and I'm gonna start introducing a bit our lab. So both of us are from the Multi-Scale Robotics Lab, uh, whose head is Bradley Nelson. And so we're doing quite a lot of things there. And as a matter of fact, we have a pretty big team. We're over 40 people now. And so we have a really wide spectrum of activities. But our main focus today is going to be magnetic actuation, but we're also involved in micro and nano robotics and all of the fabrication process associated with the manufacturing of this kind of robots. But so again, today, mainly focused on magnetic actuation. So first, let me first clarify what we mean by magnetic actuation here. Um, so I hope all of you know what a magnet is, but so I'm gonna make that assumption. So, and you may have noticed that when you submit a permanent magnet to an external magnetic field, for example, when you make two magnets interact with each other, you're actually going to have two things that happen. The magnet's going to experience magnetic force that are created by the gradient of the magnetic field you're submitting your magnet to, and it's going to experience a magnetic torque, which is coming from the misalignment between the field direction and the magnetization vector. Um, and so overall, when you think about it, you basically going to be able to control your magnet with 5 degrees of freedom, essentially 2 forces and 3 forces and 2 torques. Um, and so this is basically what the magnetic actuation consists of. You're going to create a magnetic gradient and a magnetic field, and by doing so, you are able to do a 5 degree freedom actuation. And so to do that, to be able to manipulate a magnetic object, you going to be required to control the field and its gradient precisely at any position in space. And so our approach in our lab to do that, to generate such fields, is to consider systems that are composed of current-controlled electromagnets. And you see several generations of these systems that was developed in the labs over the years, and that's what we call electromagnetic navigation system, or eMNS for short. And what, as you can see on the video here, by controlling the field and its gradient, you're able to control both the heading and the direction of the micro robot you see on the picture here. And so Simone, as I said, is going to give you a bit more details on how you design and evaluate such systems in the second half of the presentation. Now, using this machine, you can wonder, well, what can be manipulated? I mean, of course, it's understood that this robot has to be magnetics, but magnetic. But you have a lot of different things you can do there. First, you can consider rigid structures. That's something we investigated a bunch. For example, you could control like rigid magnetic modules, and you can assemble them together by submitting them to magnetic field. So you can do this kind of fun assembly process. Now it starts to get interesting actually when you are making these structure softs, because you can induce deformation of structures using the magnetic actuation. So as you can see here, I just put my rigid modules together by soft links, and all of a sudden it's already start to look pretty interesting to deform such structures. You can also start thinking about making really soft structures. You can guide them through tubes, as you can see here. So the structure is going to basically conform to a constrained environment. And you can also magnetize soft structures in a complex manner and do this kind of locomotion pattern as well that are again really interesting, and that would be very difficult to do with something else than magnetic actuation. Now, a key idea that our group got a few years back was to also fabricate micro swimmers that can propel themselves in a fluid through a corkscrew motion. So that's what you can see on the video down there. You basically submit these structures to a rotating magnetic field. You induce a rotation, and once this structure is in the fluid, it can basically propel and swim within the fluid. And well, this is very good justification to use magnetic actuation here, because it can be of course very small, and it can be, these structures can also be soft, as I mentioned before. Fun fact, that was actually at the time, well before I joined the lab, but that was at the time awarded like that was the world's smallest structure in 2012. So yeah, so a lot of what we a lot of the motivation to use these structures and the actuation strategy comes from the fact that this is a really nice strategy to do intra-body navigation and to achieve to perform medical procedures with that. And so that's also one of the focus of the lab, namely being able to functionalize these streamers, for example, to deliver drugs. In this example, actually, the idea was to functionalize the streamer so that it can perform a gene transfection. So I'm not going into the details there, but you can understand that the motivation to use this magnetic actuation is quite strong for medical applications and for intra-body navigation. So I was about to say we apologize for the clickbait title, but actually I think we totally assumed that. Our idea was to the dream, essentially using magnetic actuation, is to kind of replicate the idea of a fantastic voyage where well, you can have very tiny structures that are highly functional that you basically can go through the blood and cure a disease. Now, I still had a question mark because we're all scientists, so we know that we're not living in an ideal world here. So there is a few details that had to be worked out for that. Now, a consistent story we put together a few years back was to consider that to deliver these functional microstructures to the human body, you're going to have to have a delivery device. And so a lot of the effort we are putting into our development right now is to develop catheters that you can see here that can be magnetically guided as well, but that's going to locally deliver your microrobots within, for example, the bloodstream. And then with the strategy, you can locally deliver something, then move a little bit and release a therapeutic payload somewhere. And ideally, they can also be biodegraded autonomously after that. So I'm not today. We don't really have time to go into the details for this kind of story. We're going to focus on more the magnetic actuation. But I wanted to give you an intro as well on this delivery tool because, again, this magnetically guided catheter, or the more scientific name here is magnetic continuum robot, is also something that was used actually already in clinic, as a matter of fact. So the idea here is that you embed magnets along a flexible body, and your magnetic continuum robots basically going to align with the magnetic field, and doing so, you can navigate your delivery tool using magnetic actuation. And so one of the spin-off of the company called one of the spin-off company of our lab called Aeon Scientific, back in 2010, they actually put together a system to perform cardiac ablations using magnetic catheters. So the strategy in that case was to demonstrate that you can navigate within the human heart and then reach some target and perform ablations, but so basically burning tissues to prevent arrhythmia in the heart. And so that was a completely viable option to manual catheters, and actually a much safer alternative, thanks to the softness of the tools that were used. So we keep doing a lot of developments using these kind of tools. We extending, of course, the features of this delivery of these continuum robots. We're doing variable stiffness for them. We are trying to navigate through the vasculatures. We're doing a lot of ophthalmic surgeries applications. We're still doing ablations. You can see here two examples, both for the cardiac and for the to cure retinal diseases. So yeah, that's I think that's a nice overview of the kind of application we're targeting and still working on so far. Now, again, we have limited time today, so usually these are, I would say, the three main components of our research. In terms of application, I'm not really going into the details today, but I give you already a broad overview of that. In terms of technology, Simone is going to get back to the design of the electromagnetic navigation systems in the second half of the presentation. And I'm going to focus in the rest of my part to more the fundamental research we're doing, and mostly on the modeling and control of these tools and of the electromagnetic navigation systems. So the first part we are actually interested in terms of modeling is the modeling of the electromagnetic navigation system. So the big machines that's going to generate the field. So remember, to generate the field, we basically need a set of current controlled electromagnets. So the system you see here is called the cardiomag. It's a fairly big system composed of 8 electromagnets. And you can imagine that to be able to generate a field precisely at any position in space, you want to be able to model and predict how the field that is generated at this position is related to the currents that are going through the coils. A pretty straightforward approach to do that is using a linear approach. So essentially consider that each of your electromagnets is just a dipole source. So yeah, basically the field that's going to be generated also by just a point dipole point magnet. And to predict what the field's going to be, you just superpose all of the contribution from all of the coils. So you have something that looks like this. Your field B at position P is going to be related by the currents in each of the electromagnets stacked in the vector I, and the relationship just going to be what we call an actuation matrix that we call A, and that depends on the position P. Now, if you want to control your field at a specific position, well, you just have to invert your matrix. So you're gonna have your reference field, so B of P star, which is the field that you want to achieve at the position P. And to know the currents you have to feed through your coils, you're just gonna use the pseudo inverse of A. Now that works most of the time. That doesn't work that well with the cardiomag here. That is a fairly big system, which when you have too high currents, you see that you have a saturation effect, meaning that the magnetic field is not going to evolve linearly with the currents anymore. That's what you can see here on the graph. To account for that, so that's going to lead to non-linear behavior, and you cannot really use your linear relationship anymore with the high currents. And so we spend sometimes proposing like strategies to account for these non-linearities. One of the approach that I'm going to mention here is the use of machine learning to actually take into account such non-linearities. And so to do that, you have to collect a lot of data. And the way to do that is you're going to have this um, array of sensors. So all of these PCBs that you see that are stacked on top of each other there are composed of magnetometers. So sensors that can sense the field in any direction in space. You're going to generate random currents, collect the related magnetic fields, and you can train a model to actually predict what the field's going to be for new input currents. And so the graph that you see here is the performance of the different models we developed at different current level. And so we tried so what we call MPM here is the linear model that I mentioned before. You can apply some saturation functions on top of that to try to account for the nonlinear effects. And the three last graphs are basically three different um, strategies using machine learning, namely using artificial neural networks and convolutional neural networks. And you can see that in both of these cases, you can achieve much lower error in terms of magnetic field. So the MAE here is the mean absolute error of the field magnitude. All right, so that's only the first part of the story, of course, because of course you want to be able to predict the magnetic field that is produced by the machine, but on the other hand, you also want to be able to predict how your magnetic tool, so in our case, this magnetic catheter is going to be deformed under such magnetic field. So maybe some of you are familiar with how people usually model elastic beams, but we essentially took inspiration from that to develop models for our catheters, for our magnetic catheters. I'm not going to get into the details there, but we also spent some time trying to understand a few weird effects that happens with magnetic fields. So one example is what happens on the video on the right hand side here. When you submit this kind of systems to a rotating magnetic field, you're going to have this snapping. It's basically instability, magnetic instabilities. You're going to have your catheter that snaps from one position to the other. And so we also investigated these kind of behaviors and trying to understand exactly what's happening there. Anyway, so here's an example of how our standard models for catheters works. So we just use a cost railroad model that is a pretty standard in the community, and you can see how a catheter is gonna behave within a realistic magnetic field produced by one of our machine. So the limitation of this first strategy is that the length is fixed and it's only in free air, so you don't really account for collisions there. And so more recently, we also spent a lot of energy trying to come up with strategies to simulate how this kind of tool is gonna perform within a constrained environment. So essentially, we want to be able to account for collisions, and we want to be able to change the length of the tool um, as it is, as a matter of fact, for a real application. And so we based our implementation on SOFA, which is a pretty powerful simulation framework that's been used for other deformable structures, non-magnetic though. So we just added the physics related to the magnetics, and we've been able to have this nice simulation environments that we could use in a lot of different contexts. So it's pretty nice. We can take into account friction forces. We can detect collisions. A pretty nice things with that is that you can also propose new models. So the idea now is to use that for in a control strategy to predict how our tool's going to deform in a given environment. And we did a few. So that's actually pretty fun. We did that So what we see on the left-hand side is the real experiment, and we try to compare that to what the simulation is going to give to us. And that was working in principle. That was working pretty well. So that's a pretty nice result for us to see how the simulation can match pretty well our experiments in a already pretty complex geometry. Okay, so now that was for pretty simple structures at the end of the day. I mean, you know, this is a bunch of magnets on a flexible beam. A bunch of fun things we're doing as well is to try to do models for more complex structures. So this is the example I gave you just at the beginning of my presentation regarding um, this array of deformable cilia. And so in that case, the fun part is that each of the cilia is magnetized in a different direction. And the pictures you see on the bottom here is how, depending on the magnetization, your cilia is not going to deform the same way. It's not going to have the same trajectory under a rotating magnetic field. And one of our work here was to be able also to predict how this magnetization going to affect the pattern of deformation. And so on the figure that you see, the red dots are actually measurements, and the blue lines are predictions from the models. And again, we were quite satisfied to see that what we're able to predict with the simulation framework is actually quite close to what happens in reality. And of course, a lot of perspectives to use that. I mean, you can generalize that to more complex soft magnetic structures. The holy grail would be to be able to simulate this kind of millipede-like magnetic structures, which is really cool, but actually really hard to simulate. So that's okay. That's more on the fun research side. But as a matter of fact, this model is also really useful for training, because remember that at the end of the day, we want these tools to be used by, I mean, eventually by surgeons to perform a medical procedure. And so these simulation tools is really useful for, well, to make them manipulate the system without really having the system yet. So you can see a little game here that we developed to for the surgeons to familiarize themselves with how they could steer these magnetic catheters with a standard joystick. And we also, well, this is actually with a real neurosurgeons, with a real neurosurgeon. And so the left-hand side is actually a real procedure, well, with a real system, but on a silicon model. So it's not in vivo, but it's in a pretty realistic model. And we can see on the right-hand side is what we are able to do with the surgical simulator. And so, yeah, again, pretty close to what happens in reality. So yeah, this is pretty much what we're doing in our labs downstairs now. Basically combining our electromagnetic navigation systems to our simulation framework to provide a full training platform for neurosurgeon in this case. All right, so that's actually the end of my part. I hope you enjoyed it. I'm gonna give the floor to Simone, who's gonna talk to you a bit more about the design of the electromagnetic navigation systems themselves. Thanks again. Maybe Simone, you can start sharing.
Okay. Do you see my slides?
Not yet.
Do you have to stop sharing yours, maybe?
Oh, probably. Yep. Go on.
You see mine now?
Yep.
Yes.
Okay, perfect. Thank you. Sorry for this inconvenience. So as Quentin mentioned, I'm going to do more from the theory that you saw before and a bit of application, like more on the really our core side of the practical aspect of what we're doing. And as Quentin mentioned, essentially our robot is a combination of the external system which generates the field and the tools that we put inside the human body, either the catheter for neurovascular surgery or the heart or so on, or a microrobot and the system outside. So my specialty is the system outside. So I'm going to walk you through one example on how we got to build one and what is a bit the learning curve behind it, because it can be pretty hilarious. Definitely was for me. And essentially, I think the first thing you will ask yourself as soon as the slide decides to change is, Quentin showed you a lot of nice applications on what is possible in the field. But we have designed a lot of system over time that could be adapted to different sizes. So we have really tiny systems that are maybe under 50 kilos to the ginormous one that you saw before, like this one that you saw from the startup from AN Scientific. It's like 10 tons. It's a huge machine, 5 cameras, and so on. But if you really look at it, there is not so much of this machine that are actually installed anywhere in a real hospital, because at the end we are engineers and we really want to turn our research in something useful, not only to make papers, but really to help the world, let's say. And a classic machine here on the right will be the Da Vinci. You probably know it is this remote robot to do surgeries. And of these, there are around 5,000 installed in the world. While if you look on the side of the magnetic navigation system, there are mainly 2 companies that provide them, or exclusively 2 companies. One will be Stereotaxis here on the top of their system. They have roughly, with all the new system, around 100 units, and AN Scientific, which managed to install 2 units and perform a small number of operations of them. And not so much other than these 2 that are really magnetic based. And while the robot trend is really increasing on in the operating room, somehow there seems that it's still a problem or somewhere a gap in accepting this kind of navigation machines in the operating room, even given the benefit that you could show, for example, with the catheter in the heart and in the neurovascular system. And one of the issues that is, or one of the things that people need to understand is that it's not so much about a question of technology, but it's actually a more integration and acceptability questions from, let's say, the medical staff, operating room, and so on. Because for most of the operations which are really complex, and we are targeting with the catheters and the microrobots, it means to transition between an open surgery, in which, for example, you open the chest or the skull, to a closed one, in which you only make holes and you enter with these flexible tools inside the human body. And the number one method for imaging, for feedback, real feedback for what you're doing on the system, is using a fluoroscope. And so essentially an X-ray machine mounted on an arm like that, that is then passed around the patients to analyze from different views, either the heart, the brain, and so on. And there are a number of angles that are required and configuration to do that. And the main issue is that if you go and look into a patient, like represented here, and the place which this magnetic machine take up, you quickly see that there are tiny machines that take up a certain amount of space. This will be the Octomag that you saw before, this 150 kilo machine with a very tiny operating space. Or if you want to be able to work on a larger area, larger volume, like for example, kidneys or the heart, you need a way, way larger machine, which really obstructs quasi the access to the patient. So if you now, for example, want to fit an X-ray because you are operating in the brain, and the X-ray will be kind of represented, the C, by this top view in red, you see that you can't really fit it or see anything because in between there is your system, so you don't get to see anything. Same story goes if you try to cut from the side, or if you want to use the same arrangement but with a large machine. So the machine really have a problem of obstructing extremely the access to the patients and the ability, for example, to fit a fluoroscope. And this is one of the crucial limitations of the machine that are currently nowadays implemented in the hospital. And all of these machines try to somehow fit the X-ray, but really always with huge limitation. And this is a huge deal for a surgeon, either neurosurgeon, cardiac surgeon, and so on, in be able to conduct the procedure in the same way as they are used now with the common end method of the open chest surgery. The main problem there, I call it a dichotomy, is that when you have a tiny system, let's say it doesn't take up so much space, this will be how we will fit one over the head, compared to a large one that takes up a lot of space. You remember in the video, you see the 2 walls here that have to open up to allow the X-ray to come in and image the patient, is that while a small system is gives relatively good magnetic fields, and good frequency of actuation, it tends to have a very, very small working space. It means the volume in which you can really generate force and torques, which are useful, are really tiny, and therefore not always that useful if you are to operate on a human. On the other hand, while we look at a system which has the volume, the operating volume, big enough, we always go in the direction of a 7-10 tons machine, which requires a lot of infrastructure to be run. You can imagine that a machine like this can easily consume maybe 130 kilowatt of power. And it's really large in volume, so most of the time you need to have the hospital designing the operating room around such a machine. And if you then add in addition that maybe the machine can only perform 1 of 2 surgeries, you are now asking the hospital to equip a whole room just dedicated to that machine, for a reserve only for 1 of 2 surgeries. And this is always not so easy to pass by to, for example, the hospital administrator, because they say it's a huge investment and they are not always sure, given how new is the technology, on the results on that side. And what I like to use is like the power density, because it's a very simple concept, like how many watt can you get out per every kilogram of the system. And you see that a tiny system like the Octomag is around 30 watt per kilogram, while a large system that offers a way larger operating volume is only maybe 7-13. And this is really the limitation, like the dichotomy, I call it. You can have a huge system which offers you a large operating volume, or a way smaller system, but then even the operating volume gets way smaller, reducing a lot what it can be done. And this is a bit why there is no good solution at the moment on the market that can be really used to do a variety of things and not be ultra specialized in one type of operation. And the reason why this is very simple. Whenever you have an electromagnet, there are 2 main driven factors. One is, for example, if you take Biot-Savart to predict the field, the magnetic field, you remember in the initial slide, I think slide 3, Quentin had showed how both the force and the moment are directly proportional either to the field or to the gradient, and the field itself is directly proportional to the current. So you want to have the ability to put in all the current you can in the electromagnets. But on the other hand, if you put very high currents, you then enter in a limitation of how much heat you are able to remove from the electromagnets. So if you put too much coils to the wire, they will simply melt and short out, and you don't get any field anymore. You will actually end up destroying the machine. And the limitation on the heat runs is really what is the maximum temperature you can allow inside the magnet, and the area mostly that is in contact with the fluid or the coolant that you're using. And these 2 topics are really the critical aspects in which define how good is your electromagnets. In addition, you should also consider the volume, because we have the radius here, which is the radius of the, let's say, of the imaginary winding of your coil. And you can, of course, increase the radius, but you have then to be careful on the volume and how the field propagates in space. So when you think of that, you say, okay, I should just create a system which I can put in all the power I can and then remove the heat. The main issue is that while that is in theory the case, when you want really to design something which is practical and not simply lab exercise, you need to take into account way, way more things, which then really go and constrain your design. For example, okay, one classic will be how much power can you drain from the hospital? You can't have infinite power or infinite current. And when you talk about 130 kilowatt, we are already talking with a very, very specialized installation for the hospital, which if they are not building your new operating room, but you want to use one which is already there, you need to take in consideration. Another very simple and stupid constraint is how big can the system be to go, for example, through the doors? And how heavy can it be so that the floor sustain it? Because if you don't, again, design the operating room from zero, or you're not like building a new room like they do when they install a new MRI, for example, you need to be able to go through the current operating room and install the system in the current operating room with all the limitations that come with it. And these are all requirements that really then kind of puts severe limitation on what you can do. For example, you cannot have very heavy magnets. You cannot pull so much current. So the question is a bit, what is the trade-off that you need to really manage to do that step that brings the advantage of the magnetic navigation system in the operating room, but also can cope without having a ginormous machine, which is very intensive from the infrastructure side, maintenance, and so on. So we kind of come up with a pseudo recipe on how we think is the good way to design one. So fun enough, the first requirement we set has nothing to do with the field or anything, but we actually say, okay, the field should be, the machine should be movable and as compact as possible. Meaning we don't want to take too much space in the overall arrangement of the operating room, and kind of sell it or think it as an additional tool that a surgeon can bring in if he needs it for his specific operation, and otherwise can just like leave on the side. Then of course, another thing which seems trivial, but it's not, is how do you interface with the hospital? So of course you need a power cable for the power. Do you have enough power? Where do you get it? How do you get it? And for the coolant, because we'll see we use a lot of coolant to remove the heat generated by all that power. Do we have water in the infrastructure, or what are we using? Are we using air? Can we reject the heat in the room, and so on? And only then later on we go to more specifics towards what field we want. We use here at the lab 20 millitesla because it's something that by experience works well with the tool that we're able to develop to a distance of 20 centimeter. And this is somehow an average distance that let us tackle more or less all the areas of the body that we are interested in. Then, of course, this is my favorite one. Keep it as simple as possible. Remove everything which is not strictly necessary for safety of operating on a machine to make it as reliable as possible. And of course, as a last one, should be really compatible with the RA infrastructure. So if you want to be able to fit an X-ray, you should not be forced the hospital to get something specific, but your machine should be able to really fit in with the X-ray that they have already installed there. And essentially, based on this rule, we wanted to try to break this dichotomy that we spoke before and really go and design a new system that could fit this gap, that is not a huge machine, but also offers you a relatively good working volume and can be directly fitted in a standard operating room without changes. And this is like our first ever prototype. And you see that when I say simple as possible, it's really like that. It's a box on wheels. And the idea is that this box will be able to fit, or will get a standard operating bed on top of it, and the field will be generated by these 3 electromagnets in this triangular configuration. And we showed that even if we have only 3 electromagnets and they are all coplanar on the same, you are still able to generate 3D magnetic field in the working volume that we are considering. And the main idea was like, if you slide this before, we will be very close to the patient so that the magnetic field is relatively high, and we'll be able to slide in the system in any operating room, connect it to 2 water hoses. This can be straight water from the tap. You don't need anything special, and our power cable that runs behind here to the power plug in the wall. And you can imagine that, as soon as I can click on the video, that should start. Sorry, just for 1 second. So we assemble it, we started testing it, and you can imagine how happy we were. And I was like, oh man, we are so good that we managed it at the first time to get the system running. What you see here, it will be, let's say, the magnet. And here we have one of standard catheters that are used in the art. And we are just moving around a bit to see how the system responds. And this was the first ever test that we managed. I was like, oh man, so good. We are so good. Great, it works. But as usual in life, if you are not humble, you get humbled pretty quick. So I was monitoring my current values and voltage value, and this should be the voltage that runs on the electromagnets. And you see that you get these very weird triangular waves, which should not be at all the case, because we should see like completely flat line because we are putting constant DC fields there. And so very quickly we realized that we weren't so great as we thought, and we had actually messed up pretty heavily, in the sense that we started looking at the coolant of the system, and this should be, in theory, purely transparent, but you see how it actually turned out to be pretty, I say, filled up with stuff. And turns out that I kind of didn't think well at my electric design here. And essentially we created a galvanic cell that very quickly eroded the cores and created a lot of rust that ended up burning through the cables and kind of destroying the system itself. So we didn't go very far away. And you probably also noticed that the system is a box, so there is no way that you're going to be able to fit the X-ray below it, because where you want to fit the X-ray, there are actually the coils. So we had to go back to the drawing board and think, okay, what is that it's really fundamental when we design such a system? And how can we take the max out of it? And essentially, there is something that I like to always bring up, which is kind of what are the absolute designing features for an electromagnet? How do you get the best out of it? And there are three main things that we already saw partially before with the Biot-Savart law and the heat transfer. Is that one is the current. The more current you put in, the really higher the fields you can get out. And an increase in air, it's generally beneficial. But then this fights against the heat transfer, because you need to take away this heat that you bring by, and you still always are constrained by the volume, because if the coil gets too large and too heavy, you cannot anymore concentrate the field as much as you wanted, so you lose field. And on the other end, it gets easier though to remove the heat. While if you increase too much the current, it gets really hard then to remove all the heat that you are generating. So it's really like a trade-off between these three things. And in addition, you also have things like frequency response. Very large coils with a lot of windings have very poor frequency response, meaning you can't change the field so quick to change direction. And then you have the mass of the electromagnet. You remember I was mentioning about how heavy can the system be to actually be carried around. So if it's too heavy, you might actually just fall through the floor. And also the magnet arrangement can play a huge role, this triangular arrangement that we used here. So we kind of went back to the drawing board and said, okay, let's try to really push the boundaries of these three and maximize the current on one side and also maximize the heat transfer. So we really went back to the drawing board and said, okay, we know that the arrangement with three coils is good. It works, that just generates the field that we want, but it's not good that they are from below because we cannot feed the X-ray. So we said, okay, it doesn't really matter where this planar arrangement is, can be on the side, and we can adapt our mass, our transformation to generate the field also from the side. This way we get the space for the X-ray. On the other hand, you saw the corrosion, the disaster with the corrosion. So we really spent a lot of time in figuring out what was the real ideal coolant. And we did a lot of tests with different, starting from having just steel parts, copper. We tried to do galvanic cell and really look at what is the best possible coolant. And we also redesigned completely the coils. So the coils you saw before were just standard, like if you take a steel core and you wind a wire into it. Here we kind of introduced a new way to cool them, which is inspired by these bitter magnets, which are used in very large, super high field machines. And we really went full on in testing things, in which we really tried on one side to maximize the current, and on the other side to really maximize the area for the heat transfer. So you can see some prototypes in which here we built in a mesh between the layers so that the fluid can actually flow through the coil. Another attempt here was done with tubes, and we really pushed them. So in the coil that we were looking at before, we pushed around 10 amps per winding set. In this one here, I'm not sure you can read it from here, but you're already pushing 37.6. So we really tried to increase enormously the power density of the electromagnets that we had. And this is kind of the final iteration design that we got out. This is a coil which is around 30-ish kilo heavy. And you can push it up to 70 amps if you want to, while maintaining actually a very good cooling. So what you see here in the thermal image is actually one of this coil that we are running at full power, and we can maintain, given the right entry flow, which is just tap water, temperature down to the 10th of degrees on the rear. And this will be like a bit how the coil looks like. So what is interesting here is that we are putting 10 kilowatt in one of these electromagnets. And we have a power density of something like 315 watt per kilos. And if you remember the CMAG, the machine we saw before, this large one that Quentin presented there, it was only 29. So in these tiny magnets, we can really take out a lot of field. And this is due to one fact that we can cool them very well. You see that here running at 30 amps, we only get up to 25 kind of degrees, starting from around 10, which is like the entry temperature of the coolant. And we can really get out huge fields compared to other machines that we designed before at relatively long distance. So this 15, 20 centimeter, we can still operate at around 50 millitesla, which is way more than the 20 that we had originally thought of. And by taking those coil and the concept of these triangles, we started really, as I said, to try to move the coil sideways. And this is a bit what we came out. So it's again a card as simple as possible, in which from the original flat coil that we had, we kind of move them up on the side and use them to generate fields that are then used from the side, not more on the bottom, to operate with the catheters in the brain or in the heart. And the system is, as before, completely self-sustaining. So all the electronics pumps everything into this, and it can be simply connected with 2 water hoses and 1 power cable to the infrastructure. And these are some of the things that we did with it. So this is how the system looks like when you align it to let's say, a medical bed. This will be, again, the experiment with the catheter that we saw before. And we also tested things like navigating inside the brain blood vessels and go, for example, and fill up aneurysm. In this other example, we go with particles, like instead of having a catheter, it's more in the direction of the microrobots, in which we release particles and then we focus the field in specific point. And by doing that, we trap the particles and use them to coagulate real blood. So this is that you see here is actually real blood that is flowing in our model. And through the use of the magnetic field, we go and concentrate this iron particle in different spots to help for the coagulation and kind of to seal up the aneurysm. And what is interesting, like if you ask me, why do you want to do it, is that, for example, you can see here that we enter through the basilar artery and we really go through the whole circle of Willis, which is something that nowadays by hand is actually not possible. So to do this kind of operation inside the blood vessel of the brain, they will have to kind of cut open the skull of the guy and do it from the outside. And this is what the benefit, the additional dexterity that such a system brings to the game. And after having kind of quantify well the system, this is a bit a comparison with the table we saw before. You remember that we're talking about the power. You see that the MagHead, this is how we call the system, that doesn't really use so much more power than other system. It's only 32 kilowatt at the moment, but he has a way, way higher power density in the terms of really watt per kilograms. And this is thanks to these new electromagnets that we designed. And we also feature something that I call accessibility. You remember we spoke about the X-ray, in how many directions you can come. And essentially what we can do now is that because the system takes out a very tiny volume, depending if you put it on the top, like when you're operating on the brain, or on the side, if you're aiming at the chest, for example, your fluoroscope arm can really now come in any direction that you want without impeding any access. And this is extremely beneficial from the surgeon, because essentially for him now, he can exactly repeat the same type of operation that he was doing before, exactly with the same X-ray arrangement and so on. And the system only brings in an additional value in terms of dexterity. How much can it steer the catheter, and how complex can be the path that it takes. And it really, but the core operation is still the same. And I think with this, we are just a bit long with the time, I guess. I would like to thank you all for the attention. And I think we have a few minutes for question, if I'm not wrong, Joelle?
Yes, we have.
So if anything was not clear too fast or completely stupid, just please let us know. And we are happy to have a chat on it.
Thank you very much, guys. Are there any questions? Yeah, Emilio, you have one.
Yeah, thank you both for the talk. Now, so Simone, you were mentioning a lot of requirements on the accessibility, power, things like that, but mostly from the infrastructure point of view, right? So,
definitely.
How about the patient's point of view?
The thing is, we didn't really mention it so much here, but the whole goal, or one of the really important aspects of having such a system instead of doing by hand, is that the surgeon is extremely exposed from the X-ray. The patient is not so bad, because maybe if you do like for an aneurysm, you go maybe once or twice in the operating room, and you heat up that dose of radiation from the fluoroscope, but it's not so bad. On the other hand, for the surgeon, we know some surgeons that maybe perform 150 such operation every year. And when they do it with the catheter, they are there in the operating room with the patient, very close to the X-ray source. And there are studies that shows that that can be a factor in, for example, tumor formation in the head of the surgeon. So with this system, they can essentially sit outside in a control room, do everything remote and kind of protect much more themselves from the dose of the X-ray from the fluoroscopy. This is maybe the main advantage from the human side. For the patient, it's actually kind of indifferent, because one advantage is that these tools that we use are much softer, so there is no risk of perforating any type of blood vessel tissue, because they are really soft, and it's only the magnetic field that really lets you steer them around. So if you push too much or anything like that, you can't really go through like it could happen with the manual one. So there is a bit of increased safety also in that direction.
How about the super strong magnetic fields and things like that?
The thing
any
is,
precautions or potential side effects on
the
patients?
thing is, we operate in a range of fields which, let's say, go from 20 millitesla to around, let's say, 200, and this is still maybe 10 times lower than any MRI. So in an MRI,
so it's
you
lower
get,
than MRI.
yes, you get maybe 2 Tesla in a kind of not super good one. So it will be the lower end, and we are max around 200 millitesla when it's really high field. The largest issue will be if you have a pacemaker. I wouldn't suggest you to use this machine, but this will be the only limitation. Even if you have a prosthetics, like an implant or something, it's fine, because most of them are titanium. We use very low frequency, so there is no no induction that can heat it up. So it's perfectly safe. And even if the machine fail, and this is one of the cool things, essentially you can just pull out the catheter and continue from manual one. There is never a risk that the machine can injure the patient itself.
I was thinking of that, what if you lose control of
we actually did some tests in which we just cut the power, literally chop it, and we see what happens. Essentially the catheter just kind of gets soft, you pull it out, put in your normal one, the manual with the pull wire, and go ahead with that.
Because at that point becomes softer, so we can just pull it out with no damage to the tissue.
Exactly. It's the standard way on how, when it's done by hand, they just kind of make the catheter soft and just pull it out from the body.
Maybe the other thing you could mention is that what we present here, I mean, our strategy for the electromagnetic navigation system is to have electromagnets. You have other strategies where people use permanent moving magnets around. And the problem is that these ones cannot be switched off. So our argument for our strategy is that actually, if you have a problem, you just cut the power and nothing is moving. You don't have any more magnetic field.
Cool.
But definitely the requirements that you were mentioning before are, in my personal opinion, the number one limitation why people simply don't want a 10-ton machine that can do 2 operations. If you can just go in with like an accessory to the operating room, which can be like the laser they use, or any other thing, and you just bring it in, put it in, they use it, and then take it out when you don't need it. This is kind of in my opinion, the way to get it to accept such a system. May really want to try it and test it to really see the benefits on what it can do. Of course, my vision.
But still, from the point of view of a layman, which I am in this case, is seeing a lot of requirements for accessibility, infrastructure, the hospital and things. I'm seeing, it's funny that there was no mention of what it does to people, right? I mean, having the patients and the doctors as part of the requirements, in a sense. Then, yeah, I understand that maybe that's not the driving. These are taken care kind of implicitly by your technology, but
let's say we don't mention it because we maybe assume it, but that's a cool thing about that's why I like magnetic field. You are essentially transparent to it. So unless they are extremely strong, which is very hard to generate them, especially to change direction if you need to, you don't care, your body doesn't care. So it's inherently safe. And this is why we think it's worth to proceed with such a technology.
Yeah, I understand. Thank you.
Are there other questions? I have one, actually. So you showed us a lot of tests and so on, and it's just a curiosity. Do you have to take something particular into account when you're testing these over many edge cases, or is it even feasible in Switzerland? No, okay. But is it even feasible in Switzerland to test these things, or I'm asking this, Simone, because I know some of your story that you go back and forth from other countries with these big machines. So I kind of wonder, what's the testing procedure until you get to use it in reality? what kind of guarantees you have to give to the
so
society.
Essentially, before you can get to any human, the machine needs to be certified following MDRs, medical regulations, in which you really have to show a lot of documentation on how your quality control, on everything from the hardware to the software. So that still takes time. The first, generally how we proceed is we do first test on models like Quentin showed. The next step then is ex vivo often, in the sense that we get like a dead part of something, like you can get it from the butcher, for example. Could be, for example, intestine of a pig or brain of a pig or something like that. Then if it's really promising, you go towards animal trials, and most for that we have partners like Unispital, we have Bern, which is one of our partners, the hospital in Arau, and so on. And if that at that point it's really like perfect, like you're like super convinced, then the general idea is that you need then to go and look what do you need really for the to certify the system to be able to ever go in a real human case. I think maybe Quentin can add something on it. He's also kind of looking into this a lot. I don't know if you have more details.
No, I mean, you're right. It's I mean, actually quite, it's kind of reassuring that you have to go through a lot of different steps to certify something like this, because it's obviously a complex medical product. But yeah, I mean, as Simone said, I mean, it's a lot of paperwork. That's the conclusion, I guess.
Then I think maybe but some of the tests we show are to the direction that you really want to maybe qualify the machine for a medical product, and some other are because you are an engineer and you really want to see what's the limit of your machine. So not always all the tests are for the same reason. Sometimes you just want to have fun.
Actually, the funny part on the design side is that you spend actually more time trying to account for unusual cases, like, you know, dealing with errors and unexpected situations rather than the normal behavior of the machine. And that's interesting, not to say frustrating, on the design.
Yeah, that's common to many engineering applications, I think.
Yeah.
All right, thank you very much. Are there any closing questions? Doesn't seem so. All right, thank you very much, guys. I think you gave your coordinates in case people want to reach out for thesis, specific questions, or whatever.
Well, thank you for having us and for listening to us for 1 entire hour. I hope we didn't bore you too much about
it. It was interesting. Thank you. Thank you very much, and good luck for your work. And to the listeners, see you all next week for the next Autonomy Talk.
Thank you, guys.
Presentation. Thank you, guys.
Thank you.
Thank you. Bye-bye.
Bye.